So the core is still contracting, the helium core still contracts, but the outer layers are pushing outwards, right? And the shell is producing energy, so that's why the luminosity increases. So the helium, it can eventually fuse, but it can't fuse into, you can't take two things and fuse. If you take two helium atoms and you fuse them, you get lithium 8, which blows up pretty instantly into two helium atoms. Um, that doesn't it's not stable. You would end up needing to lose a particle somewhere. But three of them do. Three of them will fuse into carbon, and that releases energy. But that requires a much higher temperature, but not just because it's helium, but because you have to put three things together in the same spot. So as the temperature in the core increases and as it contracts, eventually you'll get a stable helium fusion, and that will work for a while. So, you know, when degeneracy pressure is supporting the core, that's usually in the shell burning, that's that's going to, you know, prevent the collapse regardless of the energy produced. And so the temperature is going to keep rising, and eventually that temperature causes an expansion outwards. And so you get that in the core of the star, you'll have a core it's fusing, and you'll have a shell around it of hydrogen it fuses. And then the star can be stable. Right. And so what happens is, right, the star grows in size and it reddens until that helium starts to fuse. And once it starts to fuse, then the star can kind of contract back. It can reach a more stable state because the outer layers are expanding outwards. And this may happen several times over the course of the helium fusion. Right, and that's what we see in actual populations. We see this increase, and then as soon as the star produces helium fusion, then it contracts back down to what's called the horizontal branch, which is, populations of giant stars that are now stable. Right? So the actual death occurs when this helium fusion stops, when it runs out. Because again, you're trying to fuse a fraction of the total helium in the core. But eventually that runs out, and then a further contraction has to happen, and you're left with remnants at this point. So what's pictured here is a nebula. We're going to talk about nebulas a bit. I have a supplementary PowerPoint you can look at. I'm not going to go through it because it's just pretty pictures. They're really pretty. Go ahead and look at it. And so what happens is this contraction after the initial helium flash is going to be where the star sits stationary for a bit, fusing helium with hydrogen shell burning. Eventually that runs out and the outer layers contract, and you're going to get layers of the outer core of helium are going to start to fuse where they hadn't been fusing before. So you essentially get two layers, a hydrogen layer and a helium layer at fuse. And you're going to get a re-expansion, and you're going to get several of these instances of layers starting to fuse, but they don't lead to a stable state. And so you get several flashes that go on over and over. Right. So you get this sort of onion, double shell burning, and it just produces energy in spikes. It doesn't come to an equilibrium. And every time it spikes, you're going to have matter pulled up from the core. It's going to be dredged up, and it's going to go to the surface. And these spikes are going to push the outer layers away over time. So here's a diagram of the different layers, and this is a good stopping point for the video again.